All right, so I promised we would do an example of some row operations to get a matrix into reduced row echelon form. And we're also going to do an application from class, which is finding the inverse of a matrix. So I want to look at these examples today. So I've got two matrices that I'm interested in. One of them is this 3 by 3 matrix A, which has a row of ones, a row 1, 2, 3, and a row 0, 1, 1. And a really similar matrix B, not similar in the technical term, which we'll talk about later, but it just visually looks a lot like A, except the last entry of B is a 2. And you might notice that the second row of B is the sum of the first and the last row, and that's on purpose. And A is a little bit different. So we've got some questions we could ask about these matrices, like is A non-singular? Is B non-singular? And if so, what's the inverse? And one of the things that we've proved is that, for instance, A is non-singular, so A inverse exists if and only if the reduced row echelon form of A is the identity matrix. But we also saw that going through some of the parts of the proof, we came up with kind of an algorithm for figuring out what A inverse is. So, we can answer the question, is it non-singular, by row reducing it, but we can do even better if we take the matrix. Let's consider the matrix that's got A on one side, so 1, 1, 1, 1, 2, 3, 0, 1, 1. And let's put the identity matrix on the other side, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. If we can row reduce A down to the identity matrix, and we simultaneously do those same operations to the identity matrix, we're going to find that that is what A inverse is. And that was a consequence of the proof that we had for showing how to reduce A down to the identity matrix. So I want to talk through a little bit of the strategy for what I'm going to try to do in these row operations. So my goals when I'm trying to get into reduced row echelon form is I want to get, if I think about my matrix as, looking like that, in this case it's augmented, I want to get a bunch of zeros wherever I can, sort of at the bottom. And once I get zeros beneath these leading ones, or beneath these pivots, these leading entries, I don't want to mess with them. And then once I've got those zeros, my next goals are to start like building some zeros up here. And then, my leading ones are going to live in that little, I don't know, I think of it as the leading one staircase, right? So first I'm trying to get some orange zeros, then I'm trying to get some, then I want to get some green zeros. And then we'll see what happens on the other side. If we can get down to the identity matrix, we're going to get an inverse. And if we get a reduced row echelon form matrix that's not the identity matrix, we can conclude that there isn't an inverse. So let's see. What I might do is start by taking, let's say, row 2, and I'm going to add -1, row 1 to it. So let's do a row operation here. We're going to do row 2 plus -1, row 1 to row 1. So that's a type 3 row operation. And my goal, as I said, is to try to get some zeros in good places. So on the left, rows 1 and 3 don't change. I'm changing, and I meant to, sorry, I'm sending that to row 2. So row 2 is going to change. Same thing on the right, those rows of the identity matrix don't change. But row 2 is going to look a little bit different now. So I'm subtracting a 1 from the first one, so I get a 0 in that position. I'm going to take a 1 and subtract it from a 2, and I'm going to take a 1 and subtract it from a 3. So my new row 2 is 0, 1, 2. And on the other side, I'm subtracting row 1 from row 2 in the identity matrix as well. So I'm going to get a -1, 1, 0 over there. All right, let's do, okay, so now I've noticed that in terms of my strategy, like I've got my first leading one up top is looking pretty good. I've got some zeros where I want it. And so now I want to try to like zero some stuff out in the second column. So I think probably what I'll do, what looks easiest to me is I'm going to take row 2 plus negative row 3 in this case, and make that my new row 2. And then I might switch some rows around after I do this. So when I do that, the only row that's going to change is row 2 again. So I've got my 1, 1, 1 across the top, and then 1, 0, 0. The bottom row is still 0, 1, 1, 0, 0, 1. And then what changed is row 2, I'm subtracting row 3 from it. So my new row 2 is going to be 0, let's see, 1 minus 1, also 0, 2 minus 1 is 1. And on the identity matrix side of this thing, I've got negative 1, 1, negative 1. All right, so I've gotten down to that, and I'm looking pretty good. I'm noticing that I'm getting some good stuff happening here. I have introduced another 0 in that column, so I probably don't want to mess with that 0. And then I can start to, let's see, I can try to, maybe I'll try to get rid of, it looks like I could probably get rid of these ones up top if I subtract the third row from row 1, and then I can probably do some other good stuff. So let's keep plugging away here. Sorry, the sound effects are mandatory. All right, so let's take, I don't know, at this point it sort of looks tempting to take row 1 and add negative row 3 to it. So let's just do that. We're going to start zeroing out some of the top stuff, and then we'll be able to clear some things out. So let's take row 1 minus row 3. I'll write it as plus negative row 3 just to make it clear that we're doing a type 3 row operation here. The scaling factor is negative 1. So row 1 is going to change for us finally. We're going to get up top, we're going to get 1, 0, 0. And then on the identity matrix side, we're going to get 1, 0, negative 1 when we add those together. And then row 2 and row 3 from the last step stayed the same. So 0, 0, 1 and 0, 1, 1 on the left side. And on the right side, I have negative 1, 1, negative 1, and 0, 0, 1. Okay, we're almost there. Let's take 3 plus negative row 2, make that our new row 3. And the purpose of that is I'm trying to get rid of that little entry there. So that's going to take care of that for me. And let's fill in our matrix. So the only thing that's going to change here is row 3. So row 1 is still 1, 0, 0, 1, 0, negative 1. Row 2 is still 0, 0, 1, negative 1, 1, negative 1. And row 3 has become 0, 1, 0. And if I add negative row 2 to row 3 on the other side, I'm going to get 1, negative 1. And okay, let's see, can I do it? Negative, negative 1 is positive 1, so that becomes a 2. And this is almost now in my reduced row echelon form. I see that I just need to switch 2 rows around. I need to switch rows 2 and rows 3. So whoop, here we come. Row 2 and row 3 are going to swap. And what we get is 1, 0, 0, 1, 0, negative 1. We switched rows 2 and row 3, so both of those are going to change. So I get 0, 1, 0. That was my old row 3. And my old row 3 on the other side was 1, negative 1, 2. And then row 2 gets moved down. So I get 0, 0, 1, and negative 1, 1, negative 1. And I see some good stuff happening here. I've got reduced row echelon form on this side. Well, actually, the whole matrix is in reduced row echelon form. Those are my leading ones, but it looks like the identity matrix over here. So this is the reduced row echelon form of A on this side. And that tells me that this, as long as I did all of my row operations correctly, should be the inverse of A. And I'm probably going to have to check that to make sure that I believe I did that correctly. So let's let's see if we believe it. Let's try taking, let me be a little less optimistic. Let me call this thing C, which is a name we haven't used yet. Let me check that AC is the 3x3 identity matrix and that CA is the 3x3 identity matrix. So let's see, let's take a look at A. I remember what A was. We have 1, 1, 1, 1, 2, 3, 0, 1, 2. We multiply this by 1, 0, -1, 1, -1, 2, -1, 1, -1. I really hope I did this correctly. I had some caffeine today, so you know, there's a shot at it. When I take 1 times 1, I get 1 plus 1 minus 1, so that's going to give me a 1 in that entry. As I'm doing my matrix multiplication, that 1 times that 1, that gave me a 1. I had 1 times 1 plus 1 times 1 minus 1 times 1, which is 2 minus 1, which is 1. Woohoo! All right, so then let's go to our next row, and this looks like it's going to give me a 0 because I have 0 and then minus 1 and then plus 1. So that does give me a 0 in the next spot. Oops, wrong. Writing implement. We should get a 0 in the next spot, so let's check. We're going to take the first row times the third column. I have -1 plus 2 minus 1, which is in fact 0, so that's good. I do get a 0 here. And we want to keep checking this out, right? So I'm going to take 1, 2, 3 times 1, 1, -1, which gives me 1 plus 2 minus 3, which is 0. And then 1, 2, 3 times 0, -1, 1. That gives me 0 minus 2 plus 3, which is 1. This is looking pretty good. And then 1, 2, 3 times 1, -1, 2, -1. This gives me -1 times 4 minus 3, which is 0. Okay, I'm feeling better about this, but let's make sure I got the last row correct here. So I have 0, 1, 2 times 1, 1, -1, which gives me, oh, that's not looking so good, is it? I get, what did I do wrong here? Let's see. So I switched these rows. 0, 1, 2 times 1, 1, -1. This is giving me a -1. So I see that this last row is incorrect. I must have done something wrong here. All right, so we'll pause for a second. I'll go back and figure out what I did wrong. This is the value in checking our work. Let's see what happened. Aha, so good news. I didn't make a mistake in my row reduction. I made a mistake in copying down the matrix A. So that last row of A, whew, I was worried there. That last row of A should be 0, 1, 1. So I've got to fix that last entry, which I had made a 2, but that was our matrix B. Okay, so now this is going to work out, and I get 0 and a 0 and a 1. And if I do the matrix multiplication the other way, which I just did to make sure while I was not recording, if I do 1, 0, -1, 1, -1, 2, -1, 1, -1, and I multiply that by the matrix A, correctly written this time, I also get the 3x3 identity matrix. All right, so we found out that A is indeed non-singular and that this matrix C is in fact A inverse. Woohoo! Insert the sounds of, you know, a crowd cheering. The other thing that we know about the matrix C from what we did in class is that, in fact, we could write C as a product of elementary matrices. And let's look back and see which elementary matrices we get as we do this. So our first row operation gives us the elementary matrix. I take the identity matrix and I do row 2 minus row 1 becomes row 2. So I have 1, 0, 0, -1, oops, -1, 1, 0, 0, 0, 1, which is the same thing I got in my first step. That's not that surprising. This next elementary matrix that I get, I take the identity matrix and I take row 2 and subtract row 3. So I've got the first row of the identity matrix stays as is. Row 2 becomes now 0, 1, -1, and row 3 is row 3 of the identity matrix. the third row operation, okay, I'm subtracting row 3 from row 1. So I'm going to get 1, 0, negative 1, 0, 1, 0, 0, 0, 1. That's my elementary matrix there. Row 3 minus row 2. Okay, we're getting a bunch of stuff here. I'm working so hard, my Apple Pencil battery is dying. Row 1 is the original row of my identity matrix. Row 3 is changing, so row 2 is the same, 0, 1, 0. Row 3 becomes 0, negative 1, 1. And then the last elementary matrix that I have is the type 1 elementary matrix, where I just switch 2 rows, so 1, 0, 0, 0, 0, 1, 0, 1, 0. And now I can write C as this product. And I'm doing these in a specific order here. So like the rightmost matrix that I got was that first matrix. So I can sort of start, if I want to start on the left, the last matrix I got was 1, 0, 0, 0, 0, 1, 0, 1, 0. And then I multiply that by the previous matrix in my row operations. 0, negative 1, 1. And I multiply that by 1, 0, negative 1, 0, 1, 0, 0, 0, 1. And I look for my, so check, 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 keep going back up the list. 1, 0, 0, 0, 1, negative 1, 0, 0, 1. And the very last matrix up top is 1, 0, 0. I should just copy and paste it, but I'm not gonna. 1, 0, 0, negative 1, 1, 0. And then 0, 0, 1. And as long as I wrote all of those down, I should be able to multiply all of those together and show, I hope, that that gives me the matrix up above. That's C. Okay, so that's an example of doing these row operations. Now, if we did basically the same thing to B, okay, so we can conclude, in this case, that A is non-singular, and A inverse is this matrix C that looks like 1, 0, negative 1, 1, negative 1, 2, negative 1, 1, negative 1. Okay, now what happens if we look at the matrix B? So let me grab the matrix B, and in fact, I'm just going to grab this matrix and fix the last entry. So let's copy that guy. Come on, copy. Start a new page. Paste that. So now we want to know if B is non-singular. So we're looking at matrix B here. Well, that's not a B factorial. I don't know how to take the factorial of a matrix, so I'll just say on to matrix B. And the only thing that was different between the matrix A and B was the last entry, right? That last entry became a 2. So I want to do the same thing. I want to think about what happens when I reduce this matrix. So let's take, I'm going to take row 2 plus negative row 3 to start off and make that my new row 2. And when I do that, I get 1, 1, 1, 1, 0, 0. Row 2 is changing now. I'm going to get 1, 1, 1. And I'm going to get this row 2 is going to look like 0, 1, negative 1. And row 3 didn't change. That was 1, 0, 1, 2, and 0, 0, 1. And now I'm going to take, let's take row 2 and add negative 1, row 1 to it. So I'm going to take row 2 plus negative 1, row 1, make that my new row 2. So row 1 stays the same. Row 3 stays the same. Row 2 becomes a 0 row in the first part. Well, it starts with 3 zeros, and I take row 2, I'm subtracting row 1 from it, so on the other side I'm going to get negative 1, 1, negative 1. Oh, and I added an extra 0 down at the bottom of that row. Bad, Professor Gibbons. Here we go. Let's put a 1 back there. All right. Now I want to get this into reduced row echelon form. So I'm going to put that 0 row down. I'm going to get all those zeros that started there down at the bottom. So let's take row 2 and swap it with row 3. And we get 1, 1, 1, 1, 0, 0. These two rows are switching, so I'm going to get 0, 1, 2, 0, 0, 1, and 0, 0, 0, negative 1, 1, negative 1. I'm not quite in reduced row echelon form yet. I see that I've got my leading ones, so let's highlight our leading ones here. Here's a leading one, and I've got zeros below it. Here's a leading one. I've got zeros below it. I guess this is going to become my leading one in that row, so I'm probably going to multiply that by negative 1. But those are the pivots in this matrix. And I now need to kind of make sure that this thing is in reduced row echelon form. So I'm going to need to cancel off some stuff above those. So let's kind of finish this up. But I think you'll believe me that on the left side, I'm not going to get down to the identity matrix. That the left side, if I just look at the first 3 columns, I'm going to get a matrix in reduced row echelon form. That's not the identity matrix. And that means that this matrix B is going to be non-singular. But let's actually finish it up. So let's see, I want to take row 1 and I want to add negative row 2 to it to cancel off the 1 above my leading one in the second row. That's going to be my new row 1. I'm going to have 1, 0. Oh, my row 1 is changing, so let me do that in orange. 1, 0, negative 1. And I'm going to get 1, 0, negative 1 up there as well. Do I believe that? I think I do. Row 2 is not changing, so now I have 0, 1, 2, 0, 0, 1. Got my 0 row down below, and negative 1, 1, negative 1. So at this point, I see that my reduced row echelon form of the matrix B is not equal to the 3 by 3 identity matrix, and therefore B inverse does not exist. So B is singular. Now, since B was singular, what that really tells us is we don't actually care about this side of this matrix, right? Because there's not going to be anything over there that we could use to, you know, to like multiply with B. There are some cases in which you might want to know what that matrix is. We might call this, sometimes this is called like a pseudo inverse or something like that, which is saying like it's what happens to the identity matrix if you perform the same row operations to it that you perform to B to get B into reduced row echelon form. But for us, because B inverse doesn't exist, because B is singular, we don't really care what happened to the identity matrix. So we can ignore that, which is also kind of nice. If we had some typos on that side, we don't really need to worry about them. And you know me, I love to make my typos. So that is an example of some row reduction and finding the inverse of a matrix using some of the theorems that we proved in class.